Let's practice naming alkenes. The first step in naming an alkene is to find the longest carbon chain that contains the carbon-carbon double bond. This is not necessarily the longest carbon chain in the molecule, it's just the longest carbon chain that includes the carbon-carbon double bond. Once you have found that longest chain, you're going to number the chain in such a way that it gives the carbon-carbon double bond the smallest possible number. So in this particular example, we're numbering from the right side to the left side so that the double bond is located in between carbons 2 and 3. You don't want to pay attention to the position of the other substituents at this point. So for example, the methyl groups in this case are ending up on a pretty high numbered carbon atom. That doesn't matter. The most important thing is that we give that double bond the smallest possible number. And once we have our carbon chain numbered, then we're going to begin naming the molecule. Now, if the molecule has cis, trans, or easy stereochemistry, you're going to start the name off with that. This particular molecule has the trans stereochemistry, or we could also say it has the E stereochemistry. Once we have the stereochemistry identified, we're going to locate and name substituents in alphabetical order, just like we normally do. This molecule has 2 substituents on carbon number 4. They're the methyl substituent, so this would be 4,4-dimethyl. And then what we do is locate the position of the carbon-carbon double bond. So this is confusing sometimes for some students. The carbon-carbon double bond is between 2 carbon atoms, so what exactly is its position? To locate the position, we just indicate the lower numbered carbon atom of the double bond. So this double bond, which goes from carbon 2 to 3, we say that its position is carbon number 2. That's what this 2 represents. And then we're going to name the parent chain based off of the number of carbon atoms in the longest carbon chain. This is a 5-carbon chain, which we know to be a pentane. However, a pentane is a 5-carbon molecule with all single bonds connecting the carbon atoms. Because this is an alkene, it has a double bond present, we're not going to call it pentane anymore. We are going to call it pentene, with pentene, the ene suffix, telling us that there's an alkene present. So we're changing the ending of the name from ane, which we reserve for an alkane. We're changing it to ene, which is our way of letting everybody know that this is an alkene, that there is a carbon-carbon double bond in the molecule. Now, in 1993, IUPAC changed the numbering naming system for alkenes and said that it would be appropriate for us to place the location of the double bond in the middle of the name of the parent chain. So instead of saying 2-pentene, you can say pent, which would mean 5 carbons, and then you can say 2-ene, which sounds kind of awkward, but basically what this is doing is saying that the double bond is on carbon number 2. And even though this is kind of awkward sounding notation, there are going to be situations where this, even though it sounds funny, is way more suitable for the molecule. So you can use either one of these systems unless you're being specifically told to go one way or another. And most chemists will kind of go back and forth between these two systems of numbering at the beginning of the parent chain versus numbering in the center or the middle of the parent chain. So let's practice naming some of these alkenes. First thing we want to do always when we're naming an alkene is to find the longest carbon chain that contains the double bond. And so that would mean that when we're locating the longest carbon chain, we really need to make sure that we're including this. Now here we have sort of a tie. We could either go this way, which would give us a 4-carbon chain, or we could go this way, which would also give us a 4-carbon chain. When there's a tie like that, we want to choose the path that's going to give us the largest number of substituents. That's a rule that we haven't thought about in quite a while. It makes the molecule easier to name. We want to number the carbon chain to give the double bond the smallest possible number. Start at the end closest to the double bond. Next, we want to think about stereochemistry. This molecule has no stereochemistry because carbon number 1 has 2 hydrogens on it. So next we're going to name our substituents in alphabetical order. Substituent on the second carbon, that's an ethyl group, so that would come first in the molecule's name. 2-ethyl, 3-methyl, 1-butene, or you could say, if you preferred, 2-ethyl, 3-methyl, bute, 1-ene. I don't like the numbers in the middle of the name, so I am not going to do it this way for any of the other examples. So here's our next molecule. Here's our double bond. There's just one carbon chain in this molecule. We want to start numbering at the end of the molecule closest to the carbon-carbon double bond. Indicate the stereochemistry. This is trans. No substituents. Locate the position of the double bond. It starts on carbon number 3. This is a 7-carbon chain, which would be a heptane, but this is an alkene, so it's a heptene. Next example, here's our double bond, and we want to find the longest carbon chain that contains that double bond. Number the carbon chain starting at the end closest to the double bond. Name your substituents in alphabetical order. 4-ethyl, 2-methyl. Locate the position of the double bond. 1-hexene. And that molecule also had no stereochemistry. And here is our last example. Here's our double bond. We want to find the longest carbon chain and number so that the double bond has the smallest possible number. 1, 2, 3, 4, 5, 6, 7, 8. I almost got tricked by that carbon number 8. I almost saw this as a 7-carbon chain with 3 methyls on it. So this has 2 substituents on carbon number 2 and also on carbon number 5. They're both methyls, so this is 2,5-dimethyl, 2-octene. Again, no stereochemistry because carbon number 2 has 2 identical substituents. Now, if we're dealing with a cyclic molecule, the rules are going to be pretty much exactly the same as for a straight chain. We do want to make sure that the double bond is actually inside the ring. If the double bond is, like, let's say that the double bond wasn't in that position, but instead was somewhere outside of the ring, then we would name it as a straight chain alkene with a cyclic substituent. We won't see any examples of that for a while. We are going to number the ring to give the carbon-carbon double bond position number 1 and 2. So just like with other examples with cyclics, we get to choose which carbon in the ring is going to be carbon number 1. We want one of the 2 carbon atoms of the double bond to be our carbon number 1 and the other one to be carbon number 2. So technically when we're looking at this, we're trying to decide, should we number it this way or should we number it the other way? But either way, however we choose to do it, those 2 carbon atoms need to be 1 and 2. We make our decision 1 and 2 like that versus 1 and 2 like this based on the position of the other substituents on the ring. So we're going to choose our numbering direction, clockwise or counterclockwise, clockwise like this or counterclockwise like this, to give the other substituents the smallest possible number, just like we would normally do for any sort of numbering on a cyclic molecule. Locate and name your substituents in alphabetical order. This has 2 methyls on carbons 3 and 5. And then name the molecule. Again, we're changing the ending of the cyclic molecule from ane to ene to indicate there's a double bond. And just like with other cyclic situations we've seen before, you do not need to indicate the position of the carbon-carbon double bond because it's always going to be on carbon number 1. So that's why we don't have a 1-cyclohexene or cyclohex 1-ene. It's not necessary. So here's our only example of this that we're going to do. Again, we want to find our double bond and we want to number the double bond so that it is carbons number 1 and 2. So we're either going to number it that way in black or we're going to number it the other way like that in red. We're going to choose the clockwise versus counterclockwise based on the substituent, the methyl group. We want to give the methyl group the smallest possible number. So that would mean that we want to follow the red numbering system so that the methyl group is on carbon number 1. 1-methyl cyclopentene.